All right, so we're going to be looking at laying the foundation right now for what we're doing tomorrow. And tomorrow we're going to be doing something called linear programming. And we're going to be taking, typically it's lines, at least what we're going to be doing, and solving some real world problems that actually can be really real world. I know there's like real world problems like how many watermelons does Biff buy that really are not real world. But a lot of what we're going to do tomorrow, I think you can look at it and see, yeah, this might be something that if I owned a business, if I did certain jobs or certain tasks, that looking at different parameters or certain limitations on these tasks can actually help me actually do things more efficiently, maybe save money or reduce cost or whatever it is. It's not really calculus, but it's something that kind of feels a little like an intro to calculus without the calculus. But to do that, I need to review with you or make sure that you're solid with what systems of linear inequalities, how they result, how you can figure out what those solutions are. So if you look in your book, just to get started with this, I want to say it's maybe page 11. Turn this thing on. So if you go to page 11, I want to just practice with you a little bit, and then I might even get into just the initial application or the initial beginning of maybe what these word problems look like, and give you kind of a step-by-step, foundation for how to start attacking these. Because the word problems, I know how people read word problems. It's like blah, 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 $274, blah, 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 100 widgets, or whatever. And it just becomes a lot of words. So the strategy for reading these and examining these word problems and being able to turn them into a linear programming model is important. So hopefully we'll kind of get started on that today, and hopefully it won't be a big deal. But if you look at page 11 in your new book, it says Systems of Inequalities and Intro to Linear Programming. So hopefully this will not be a big deal, and we'll be able to roll through this real quickly. But these are the kinds of equations that are potentially going to be showing up. Not this natural log one or that parabola. I just threw those in there just for fun. But problems like this, except they'll be actually associated with a limitation in a real world problem. Like for instance, maybe somebody says, all right, like here's maybe an example. You can spend $5 on notebooks or $2 on pencils. I think this would be a better one. You have $5 on notebooks and $2 on pencils, and the amount of money you spend total has to be bigger than $10. So this would actually be a line that represents that equation. And you would have to be able to graph this line and shade it accordingly. And if I had that limitation and maybe another limitation on notebooks and pencils, maybe another limitation on cost, all these lines kind of come together and they form a shaded region. And that shaded region is where you can meet all the conditions. Now, just because you can meet all the conditions in a situation doesn't mean that that you want to do any possible scenario in that region, because there's probably going to be a certain scenario in that region that not only meets the conditions, but maybe saves you the most money, or maybe makes you the most money. Okay, so that's the kind of idea on linear programming, is to examine these parameters, graph these parameters, and find out the best possible scenario that will put you in a position for success. Because businesses fail all the time, not just because the government shuts them down, but even in a perfect economy, the businesses actually fail because people aren't intelligent. They don't look at certain conditions. They just think, hey, I've got a great product, I'm going to get out there and sell it. But they don't think that even though they might have a great product, the parameters that limit that product's sales are important, and they're worth analyzing. And that's what linear program does to an extent. And even though we might be doing some basic kind of situations in this class, because it's pre-calculus, it's not actual economics, it's not actually marketing, there's a lot of other things that come into play, but that's where we're headed with all of this. So initially, I just want to make sure that you're good on your graphing, because a lot of these kinds of graphs are going to show up. So x greater than or equal to 4, if you had to graph something like that, what would you do? What two things are you kind of looking at here? Do what?
It's going to be like a line on x.
Okay, so you have a vertical line at x equal 4, because there's an equal, right? So I can go to x equal 4 and I can draw a vertical line. And it's not dotted because it's actually equal. And most of the work we will do will have equal signs. There are very few that will be dotted on the actual linear programming stuff we do. And then what does the inequality part do? This says values of x that are bigger than that 4. Since there's no y involved, I'm really thinking more right and left. If there was a y over here, like you see in number 2, values of y that are smaller than that, then I would be thinking shading up or down, in this case down. But because it's x greater than 4, I'm going to shade to the right. And I don't care how nicely you shade. Something like this is totally fine with it. Right? Now, another thing you could do is just pick a point. Like, if you're not quite sure about what the inequality is doing, pick any x value that's not on this line. Like, for instance, if I say x equals 5, that's a true statement. So I want to shade towards that 5, which would be shading to the right. If I pick something like x equals 2, that's a false statement. If it's a false statement, I don't want to shade. So if you're ever in a situation where you have a diagonal line and you're not sure where to shade above or below, or you have a parabola and you're not sure to shade on the inside or the outside, or a circle or an ellipse or anything, you can always plug points in different parts of the region. Or even something like this. If I had a graph like that, how do you know where to shade? Do you shade like below the graph? Do you shade like in this region, or in the middle? Well, again, if you're not sure about what to do, which you very well may not be sure, you can always pick points like in different sections. And if the point in that section is true, then shade it. If it's not true, then don't shade it. And if you need to check a bunch of points, check a bunch. It's usually not that difficult just to plug a point in there and to see what's happening. Okay, what about something like this? Y less than 3. So it's horizontal because you think y equals 3, except it's technically y not equal to 3. So how do I graph the linear part? With a dotted line at 3? And then when it comes to shading, again, you can plot points in there. Like I could plug the point 2, 7 in, except there's no place to plug 2, the 7 would show up. And 7's not smaller than 3, so I'm not going to shade up here. Or you could think, wait, y, all the values of y smaller than 3? Well, that would be everything below. And again, you can shade this as easily as this. You don't have to really darken it all in or whatever. Now, when it comes to a linear graph where you have x's and y's in there, or even parabolas or natural logs, then of course I'm going to have a slope if it's not horizontal or vertical. So right there, it's in a nice form for you, sort of. Right? It's kind of in y not equal to but less than negative x plus 3 form. So slope-intercept form. So I would go to where? Go to 3 and then slope of negative 1 tells me down 1 over 1, down 1 over 1. Try to keep that slope consistent all the way through this graph. And then is this solid or dotted? Since it's dotted, there's my line. Now again, you have two options. If it's solved for y, which it is, I can think all the values of y smaller than that line. So values of y less than this would be below the curve. And I can think that way, and that's great. If I'm dealing, and I can always do that if I'm dealing with functions. I could also just pick a point. Like what if I pick the point 3, 3? If I plug the point 3, 3 in here, I get 3 less than 3 minus 3. Is 3 less than 0? No, then do not shade that. Shade everywhere on the other side of that. Or just keep plugging in points until you see the region that works. What about 4? This one's not solved for y. So what are you going to do? Do what?
Just solve for the line.
Okay, I could. Do I have to? I could just find the intercepts. And the nice thing about finding the x and y intercept is basically the x-intercept is where y is 0, and plugging in y of 0 just makes that go away, right? Right? So my x-intercept, and I'm going to do this a ton when I'm graphing these problems in linear programming, because the linear programming equations often have really ugly numbers, and setting it equal to y and trying to graph a slope of 173 over 40 is really unrealistic. So sometimes it's a lot better to just find the two intercepts and connect the line. So right here, if I plug a y equals 0 in there, the x is 2. And if I plug an x equals 0, the y is negative 5. And you can probably see from this now the slope is just up 5 over 2. If you wanted to have that, and you actually have the y-intercept. But at this point, again, keep the slope consistent. So up 5 another over 2. Solid line in this case. Just do the best you can on keeping it an actual line. Now, do I shade above or below, left or right? What are you going to do? Now, I like plugging in the origin. The origin is a great point to plug in as long as it's not on the actual line. Like, I don't want to plug in 2, 0. If I plug in 2, 0, it's actually on the line and I get a true statement, 10 equals 10. Great, I already knew that because I have it colored in there. So pick something over here or over here, and the origin's usually a great point to plug in unless it happens to go through the origin. Plugging in a 0, 0 makes all that go away and gives me a what kind of statement? False statement. So I am not shading the origin, I'm shading everything else. So I'd come down here and shade all of that. But don't do this. I see people all the time, they get to this and they go, but y is greater than or equal to. And if y is greater than, why aren't you shading that? And what's my flaw in my thinking there? Why is that flawed thinking? Because it worked great in a different problem that I had when I think y greater or y less than. I am ignoring the x a little bit, but that's not the real trouble. Let me give you a hint. Yeah, because if I move this over, it still looks like y would be greater than, but what does the negative 2 do to this problem if you were to divide by it? Switches that sign. So if you can see through that problem, which I think you can do, if you look up and you go, oh, y greater, oh wait, if I were to solve for y so that I could think, if I divide by that negative 2, it's going to make it y less than, that would mean below, and that's where I'm going to be shading on this. So be careful that you don't just jump to conclusions and see y greater and shade above. And again, you can always plug in points if you feel like you're safer that way. What about this? What kind of graph do you know that it is? A parabola? What kind of form do you like to have when you graph parabolas? Y equals something x squared. Now, does that 3, so if I have y equals something x squared, that means I should probably move that x squared over. Does that look like the right form there? I mean, does this y minus k, a, x minus h squared is correct form? So if there's a plus 3, is that the 3 that's connected to the x? It's really not, is it? That 3 really is the k value that was moved over there. So if I want to make sense of it, because it's not inside the squared. So really this should be written as y minus 3 and then just basically 1 x. That's essentially what this problem is. Are y'all able to see that? I don't really anticipate you having that issue on a test because we're dealing with linear programming, but I'm just throwing that out there. But if I rewrite that so that it makes sense to me, which now it does, where do I have a vertex? 0, 3. I've got an a value of 1. How do you like to graph parabolas that have an a value of 1? Should I use the whole lattice rectum thing? What's the other thing we did? And the cheat trick says to take the a and put it over 1 and treat it like slope one time. So up 1 over 1, up 1 over 1, and I got a couple points. And if you wanted a couple more points, what could I always do? I could just plot a couple extra points if I want, like plug a 2 in. If I plug a 2 in, I get y equals 7. So 2 up 7, and of course axis of symmetry, we'll put that there. Solid or dotted curve? Dotted, shading above or below. Based on that, y less than looks like you'd be shading below. And again, if you like plug points in, if I plug a 0, 0 in, 3 is bigger than 0, that's true. So I would want to shade towards the 0, 0, which shades below this thing. And when you shade below, don't stop here because that curve is still growing, isn't it? It's getting bigger and bigger and bigger and moving out and up. So really, you're shading all of this. And you could determine that or confirm that by plugging even something like 7, 7 in. It's still going to be true. Number 6, again, probably not going to see this because it's not a line, but do you remember how to graph a natural log? I'm trying to dig your brain out of mothballs a little bit. It's been a nice Christmas. What do you remember about natural logs? Okay, E's are exponential curves, but it is a log base E. And what's the relationship between a log and an exponential curve? They are inverses of each other. And if exponential curves grow like this, or maybe decay like this, exponential curves have horizontal asymptotes. So if they're inverses, if logs are inverses, then that means logs have vertical asymptotes. So all I need is to know the vertical asymptote, and since there's no shift, there's my vertical asymptote. If I had shifted like this, then that would be the vertical asymptote. And then I just need 2 points. What are the easiest 2 values that you know to plug into a log base E or a natural log that would you be able to plot a point? I can't log a 0. 1's great. If I plug a 1 in for x, what's the log of 1? 0. So that gives me a point. And then what other value can I plug in for x that I can simplify without a calculator? Be what? E. It's log base E, right? What's log base E of E? 1. So I can plug an E in and get a 1. And what is E approximately? 2.7. So I could go over 2.7, which is about that, and up 1. And that's all I need, is a couple points. And if I have a couple points and I know there's a vertical asymptote, what is this graph doing? Diving down. Should I make it a solid line? No. So if you happen to do that and make a solid line, since you don't have dry erase and you can't do that, then just draw a little arrow to it and say this is supposed to be dotted, or just say dotted. And then where would I shade? Above or below? Since it's y less than that. Which way? Below? Yeah, I'm going to shade below. Now, a lot of people miss this because they're thinking, wait, do you shade there or on the outside? But if it's a function and you have y, it's above or below. So I'm shading y less than that, I'm shading below. If I turn this around like that, the y greater, don't shade this whole outside part. It's not like a circle where it's inside or outside, because circles aren't functions. Right? If it's a function, it's above or below. You already know I can't even plug negative numbers into that, can I? I don't even get answers when I plug negative numbers in there. It gets D and E. So that couldn't possibly be true. It's only above or below. So if it was greater than, I would shade up in here and actually all the way right there above the curve, all the way down in there. And then, but because it's less than, I'm just shading that. All right, moving on to 7. And then we're going to get to systems. Just kind of giving you a little run through of what we've done this year with inequalities. What about this? Exponential curve. What do they always have? We kind of already said. Horizontal asymptotes. So there's no shift. So there's my horizontal. So all I need are 2 points to help me with this. What are the easiest 2 values to plug in there for x? If I plug in 0, I get y is 1. That's an easy point. And what else? Well, I can plug E in there, but what's 2.7 to the 2.7? That'd be a little harder. What would be easier than that? Plug a 1 in there. If I plug a 1 in there, I get E, which is about, so if I plug a 1 in, I get 2.7-ish. And if I have a horizontal asymptote in those 2 points, do I have much choice? No, I got to connect them and then just follow the asymptote. And this one is a solid line. And where do I shade? Above or below? Or left or right? You tell me. Above. It's a function. Y greater than, I'm shading above. What about here? Remember what 1 over x is? The broken band director, what do they call it? Maybe? I'm not dotting it because it's less than or greater than or anything like that. That's just the asymptotes. And then I always told you just mark 1, 1, and -1, -1. That's good enough for me. And then just follow the asymptotes. And this is a solid curve. Now, do I shade first quadrant, third quadrant, or second quadrant, fourth quadrant, or above, below, inside, outside? What am I doing here? I'm go all day. Help me. You can, but what are you going to shade when you plug the origin in? And it's okay, yeah, if you do plug the origin in here, you get zeros greater than undefined. So, but you can always plug points in and see what happens, but that's going to confirm that it's not graphable. But even if I plug something like 1, -1 in, if I plug 1, -1, that's not true, right? So I'm not going to shade that, but does that mean I shaded all of this and all of this? I would have to check a lot of points just doing that. It's a function though, right? So if it's a function, and I see y greater than, where am I shading? Above everywhere. So not only am I going to be above here, but I'm going to be above here. All of that. Are you with me? And if you're unsure, plug in the point -3, 3, or 3, 3, and see if you get true statements. And you will. Or you can even plug in -1, -1/2. And if you do, it's a true statement. So be careful on that kind of stuff and make sure you're okay. I'm going to skip number 9 because I'm bored with this. Let's look at next page, number 10. And this is kind of what you're going to start seeing. When you're doing a linear program, I'm going to give you a model, I'm going to give you a big equation, and it's going to have all these words and junk, and you're going to read and pull the equations out of there. And then once you have the equations, you're going to have a bunch of equations like this. You're going to graph them, and when you start graphing more than one shaded region, what do you start getting? When you graph one shaded region with another shaded region, you get overlap, don't you? And the overlap is where they're both true. So not just, if you have 3 equations, they all 3 have to overlap. That region is the region that we're going to be working with, the region that we are going to be working with linear programming. Okay? So let's start taking a look at that. Look at number 10. And I'm going to try to go more quickly here, now that I think you're probably a little bored with this. So real quickly, how would I graph that? Up 3, down 3, down 3, right 2, down 3, right 2, down 3, right 2, or up 3, over 2, and dotted line. And just to kind of help me think so that I don't have to shade so much, I don't know if you're like this, but there's a lot of shading going on when you start putting 3 equations or 4 equations or 5 equations. So a lot of times I don't want to shade everything because then it's like, oh, there's so much shading, it's hard for me to see the overlap. So sometimes what I'll do is I'll wait to the end and kind of eyeball where it is and just shade my answer. But I'm going to remind myself which way I'm going with the shading. So which way would you be going with the shading here? If it's y less than? down. So I'm just going to put a little arrow and say, all right, I'm shading down on that for now. And then how do I graph x greater than 0? Vertical line, 3, 0, not equal. So there's a vertical line, 3, 0. Now this is not a function, because it's just x, right? Vertical lines aren't functions. But it is x greater than, so where do you think you shade? Right? So I've already shaded down on the brown. Now I'm shading right on the green. So you can already see right now my overlap is this kind of triangle looking thing right here. Right? But I'm keeping it really clean by not shading everything all at once. And then finally, what's y greater than 0? Goes through y, again, dotted. And where would I shade if it's y greater? Up? Okay, so you tell me, if I'm going down on the brown, up on the purple, and right on the green, what do I end up with? Just that triangle. So I'm going to come in here, because I haven't messed this whole thing up, and I'm just going to come in here and shade that. Now, if you don't do it this way, if you do it this way, if you come in here and you go, all right, well, I went down on the brown, say you did this. And then you come in here and you go, all right, and then I went right on the green. And then you came in here and you say, all right, and now I'm going up on the purple. It just starts getting really messy to me. But you're welcome to do that as long as when you're finished. Right now it looks like you've shaded almost the whole curve. You need to come back in if you do it this way and really darken in the final overlap. So make sure you come in and darken it in so I can tell that it's that. I had a kid that would always, his name was Mitchell, he would always come back in there and erase every part of the curve. It wasn't actually in there. And he would do that. And I was like, dude, why are you killing yourself? Like, I don't need you to do all that. I mean, it worked for him. He's a 36 ACT guy. This dude, Mitchell Hughes, he showed up his freshman year. He was about 5'4", 100 pounds. Skinny little guy. Went out for freshman football. Always wanted to play football. Just got pounded. But was so resilient. Just would never give up. He was out there just... And then, but he got pounded. He goes, I just always wanted to play football. I mean, he was like it was rough from the stories I heard. But he was very resilient, always was the first guy in line, he was like the Rudy, if you've seen the movie Rudy, about this Notre Dame walk-on kid. And then his sophomore year, he was like, okay, football's not for me. I'm gonna get into biking. So not like mountain biking, but like road biking. So he got into road biking, and he started gaining, you saw his legs growing. I mean, he went from this stick figure to this dude who had these massive thighs. And, but he got up to probably 5'8", I don't know, 140 pounds, got bigger. But he came in second in the state in this road bike division as a sophomore, and all the high school staff didn't even know there was that. But anyway, so then he decides, I'm gonna get into weightlifting. Dude, by the time he graduated, he was 5'10", about 190 pounds. Like, I'm about 190, but I'm not this dude was jacked. Like, I mean, his neck went down to here. He had like a 29-inch waist. He was benching over 300 pounds at 5'10", 190. Just massive dude. Whatever he did, he always put his mind to it and did it 100%. But he was like so robotic. Like, he would sit up out of his chair, hand in his paper, and he'd like, it's like in the military. He'd walk in there, and then he'd sit and then slide in. I mean, everything was so regimented, but he did this on every graph. He would go back and erase, make it perfect. No need to do that. Anyway, I do remember he went to Alabama back when you could do this. He went on a full ride. I don't mean a full tuition like you guys might get. I mean, in the olden days, 5, 6 years ago, you would get tuition, room, board, stipends, computer, overseas travel. He made $3,000 a year on his scholarship at Alabama, and I remember he bought a vintage little Porsche when he was done with the money he saved from college that he got just as a stipend, extra money to spend. Anyway, all right, jump to. Tell you what, I'm going to jump to 14. Jump to 14, and most likely you're going to be sitting on a bunch of equations that you're going to be graphing. So if you look at number 14, help me out real quickly. First one. Up 4 with the slope of, so up 1 over 2, up 1 over 2, up 1 over 2, down 1, left 2, down 1, left 2. Dotted. Shade above or below? Below. I'm going to put a little arrow and say, okay, I'm going below on this one. Next one, x greater than negative 4. What do we have? Vertical at negative 4. Again, dotted. Where am I shading, right or left? Or up or down? It'd be tough to go up or down on this one. To the right. So since I already know I'm going down there, I'm going to the right there. So it looks like I'm over here, kind of heading towards the first and fourth quadrant, all that right there. Next graph. Down at negative 5. Slope again of negative a half, actually slope of negative a half. So rise 1, left 2, or down 1, right 2. Right? Solid line this time. And where am I shading? Up. So I've got that region, and that direction, this direction. So now I'm kind of honing in on this area right here. And then finally, down at negative 4, slope of 2. Again, solid line. And which direction would I shade on this one? Up. So, if I'm shading down there, right there, and up there, where's my feasible region? Doesn't that seem like a little bit easier plan than putting shading everywhere and trying to deduce? So right here, that tells me, okay, there's my overlap. And I can just come in here and shade that up. And if this was a linear programming model, any situation, let's just say X and Y, say you were a guy selling 2 kinds of shoes, and you had all these conditions on these shoes, like I have to sell at least this many of this one and at least this many of this one, and I'm making so much off this one and so much off this one, and I only have so much to spend, so I'm limited, but I have all these costs, and all these parameters gave you this region. Well, anywhere in here would be acceptable to you, which means like you would actually say make money. Or you'd meet the conditions that were required by your problem or your scenario. But it doesn't mean you're going to make the most money that way. Where do you think you're going to make the most money within these regions, or maybe minimize the cost? Not necessarily in the interior, but at these extreme points. So these places there, and there, those are the places where you're going to maximize cost or minimize cost or maximize profit or whatever. So your process that you'll be doing is finding these equations, graphing these equations, and then figuring out the shaded region. We call that the feasible region, because that's what's feasible, that's what's possible for you. And then you're going to find these intersection points. And how do you find intersections of these? Like if this graph right here, I'm going to call that line 1, line 2, line 3, and line 4. If this is line 1, and line 2 is right here, and line 3 is right here, and this is line 4, how would I find that point where it intersects? I'd use a system of equations with line 1 and line 4. How would I find that? Use a system with line 1 and line 2. And you're going to have a calculator on some of these, or you may. So if you had a calculator, it's really easy because you can just graph these graphs and just find the intersection points. Except you can't really graph x equals negative 4. That's a problem. But guess what? It's really easy to solve when x is negative 4 because you just plug negative 4 in there and solve for y. So it's really easy to find those points. But that's where we're headed with the whole linear programming thing. Okay? We'll do one more. What about 15? Throw in your curveball just to see if you remember anything about absolute value. But how do I graph that absolute value equation? So start down 3 and graph a what? Solid dotted. Solid, and there's no slope on that, so. And is it a function? Yep. If it's y greater than or y less than, it's a function. So it's y greater than, where are you shading? Above. So I'm just going to draw an arrow saying, okay, I'm going above on this. And then the other one, y less than 3. Where am I shading? Below. So far I have this triangle, and then finally, x less than or equal to 2. Solid line going through x at 2. And where am I shading, right or left, since it's not a function? Left. So what do I shade here? A little strange quadrilateral looking thing right there. So that's the idea of this. Now the only task you have, and I'm going to start you in the next 7 or 8 minutes just to kind of introduce it to you, but the task for you will be to look at a word problem like this, I'm going to move through that, to look at a word problem like this and actually figure out how to make the most of your possible situation. And sometimes it requires very little effort. Like we're going to do a couple problems in here where I really think you might look at it and go, that makes sense. I could have done that. And then the guy ends up saving thousands of dollars a year. And in some cases, thousands of dollars a month just by tweaking his scenario to maximize his situation given his conditions. So you're going to be given a problem like this particular problem. You got concert ticket sales, and they're selling 2 kinds of tickets. Essentially, one's cheap, one's expensive. And they're trying to make the most money they possibly can, but there's some conditions on there. Like, first of all, there's cost that shows up. One type's 15, one type's 25. And this is an old problem because concert tickets typically are more than this. But anyway, but you get a situation like that, well, you never know. That $25 ticket might be too much for some people. Like if you got a dad and he's bringing his 4 kids, he's like, oh, $150, man. I'd much rather pay 90 and go 15 apiece. We'll sit in the nosebleeds. So that might be something that comes into play. Also, it says the promoter has to sell at least 15,000 tickets. So evidently the band's like, hey, we don't even play if you can't sell 15 tickets. That's beneath us. So he's got to sell so many. That's a condition that he might have. And it says he has to have at least 8,000 of this kind, at least 4,000 of this kind. But there's only 40,000 seats in the venue. All these things are conditions that show up in your problem that you have to find a way to create equations out of. And that may seem daunting right now, but I'll give you some strategies that make it so it's not so bad. And then finally, I got to make at least this much money. So it says how many of each kind of ticket should be sold in order so that I maximize my revenue. Okay? And then once you know that, how to maximize your revenue, you start pushing tickets that way. You start marketing them in that direction. Okay? So anyway, and that's a whole nother conversation that you can have in college if you get a business degree. But here's my advice for you, because I know a lot of you are looking at this equation and all you're seeing is blah, 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 blah. So my advice to you is to start tackling these things one at a time using this kind of little sheet right here. So these are guidelines for helping you out with linear programming. And the first thing I'm going to do is I'm going to ask myself the question, what in the world am I even talking about? I think I did this with you guys last year. I had y'all read a word problem, and you read it, and I said, all right, everybody look up. And all y'all looked up, and I'm like, all right, everybody read it? And you were like, yep. And I was like, what's the question asking? And it was like crickets in here. And I think I had maybe 1 or 2 people, and this happens every year, maybe 1 or 2 people went, were they asking to find? But the irony is, that's what very few people, they read it, and it's like, ugh. They forget to actually identify what the question is before they start trying to get an answer. That's really important. So in that problem we were just talking about, were we talking about ticket prices? Were we talking about the number of tickets? What is it we were talking about? Now I know we didn't read it closely, but that's what you have to identify. So look through there and see, as you read it, look for the question that's actually being asked, okay? And I'd figure out what variables you want to use. Now, I want to be graphing these on an X and a Y plane, not an A and a B plane or an M and an N plane. So I'm always going to let my variables be X and Y to stand for whatever it is I'm looking for. But write that down and be specific. Don't go, X is cars. What about cars? How many cars? What's the price of the car? How big is the car? What's the square footage? How many cubic feet? I mean, write down what you're talking about. If you don't do that on a test, I'm not going to count it wrong, because I don't, as long as you're writing your equations. But if you struggle with word problems and figuring them out, I would encourage you to do that. Second thing, we're going to be minimizing cost, maximizing revenue, maximizing profit, whatever. That equation isn't going to be graphed, but it's going to be right in the midst of everything else messing with you. So my advice for you initially is when you read through it, identify whether we're talking about profit or cost and write that equation down. And usually it'll be a two-variable function. Like your revenue might depend on how many cars and how many trucks are in the situation. So it's not going to be like a y equals x function. It's going to be an rxy equals something xy function. And this is probably the easiest part of the equation, if that's bothering you right there. But it's saying the revenue is going to be a function of two different things. Okay? You all tracking with me? All right. So write that down, and when you're done writing it down, draw lines through that information so you don't accidentally reuse it in your problem, because it's very easy to get that confused. And then the third thing is, because I'm looking for situations that I'm going to have linear graphs that are inequalities, look for words that suggest inequalities. Like, for instance, I can have at maximum 8,000 tickets. Oh, well then the number of tickets has to be less than 8,000. Look for an equation that represents that. I have to sell at least 2,000 of this kind. Oh, the number of this kind has to be more than or equal to 2,000. So look for those words that suggest inequalities when you start to set this up, and that's going to give you an initial idea about what the equations are. And then you can start looking for, like right here, if I'm talking about pens or costs or hours of work, these are going to help me find that. Like if I said I have to have at least 300 cars or vehicles, then you'd say, oh, well, the number of cars and the number of trucks has to be bigger than 300. X plus Y is bigger than 300. So there are ways to put all this stuff together, but that's the idea as I'm going through these equations. All right? And then also, do you know what stoichiometry is?
Yes.
So stoichiometry is a way to convert units, right? Like to change feet to miles or inches to meters, whatever, using these little conversion units that are identical, like 12 inches over 1 foot. It's the same thing, even though they're different numbers, they mean the same thing. So I can use that to change units. Well, a lot of times, if I write these equations out and I write the units down, looking at the units helps me make sure that I don't have trucks equal to pens. That doesn't make sense, right? I want pens equal to pens, or costs equal to costs, or hours equal to hours. So knowing what my units are, if I get a situation and I write down the equation and I go, wait a minute, this is saying trucks is equal to miles. Those aren't the right units. Maybe I need to convert those units so that they match. So we're going to jump in this. I wanted to get a little bit further, but we're going to get into this tomorrow a ton. Make sure you understand the graphing stuff, and make sure you read through this and have a pretty decent idea. Oh, and then one last thing. When I'm dealing in real world problems, can I ever have negative pens or negative cars? So if my variables are X and Y and they have to be greater than or equal to 0, what quadrant does that always force me into? First quadrant. Because if X is greater than 0, it's shading this way. If Y is greater than 0, it's shading this way. That overlap is in the first quadrant. So you'll see on most of these equations, I just go ahead and give you that. But that doesn't mean that X greater than 0 and Y greater than or equal to 0 aren't equations. You've got to remember to write this. Y'all have a good one.